A string is a sequence of characters. Lots of times, people will say that they are an array of characters, but they're really much more than that. They are also one of the primary ways that you can corrupt memory, because it's very easy for string operations to run past the end of the space you've allocated for them. We have to use them very carefully. We've seen strings already. Every time you put a sequence of characters between quotes, that was a string. We can also store them as arrays of characters, but there's a trick to that which we have to be really careful about. Let's look at an example. I've stored the string initial value in a character array. When I dump it in memory, you can see the letters here. Yes, they are stored backwards in each word. That's because the bytes in a word are addressed in that order. Notice that the first byte after the string is a 0. Remember, in C, arrays don't know how long they are, so we need some way of knowing where the string ends. C does that by saying that all strings have to end with the character \0, which we call the null character, and it has a hex value of 0. All of C's string functions will pay attention to that null character and ignore anything after it. When we store a string, we have to make sure that there is space for that null character. So storing Merlin is cool would require 14 characters for the characters, plus one more character for the null terminator. Our printf formats have a placeholder for strings, %s. If you give it a number, your string will be right justified in that space. If it's longer than the space that you give it, it'll overflow to the right. And if you make the number negative, it will left justify your string. Well, that's an odd use of negative. It turns out that null terminator is a source of great consternation. What do you think happens if we overwrite it with something else? For example, let's watch this code in CLion. Here, I created a character array that holds the string 123. Since it's a string, it takes 4 bytes. Remember that null terminator? If we put a breakpoint here, we can dump the stack and find that string here. See the null terminator? Just to be sure it prints out correctly, I printed it out. My format string put capital X's around it so that we can be sure we know where the string begins and where it ends. Step over that and wait, there's no output. Sometimes C does not flush output all the way to the screen, so I've added a call on fflush to force it to do that. Step over that, and here's the string as we expected it. Now, here, I'm storing the character 4 in the position 3 of the array. That's where the null terminator used to be. If I look at the memory dump, you can see that the null terminator got overwritten. Step over the printf and look at that output. Remember, it's going to print everything until it finds a null terminator, so it's printing out gibberish until it runs into a random byte with 0 in it. So if a bug in our code overwrites the null terminator, we have accidentally made our string randomly longer with garbage where it goes past where it should have ended. Okay, that example seems a bit rigged. I intentionally stomped on the null terminator. Why would anybody do that? Well, it turns out that there are lots of ways that that can happen. We need another example. We've used scanf to get input from a user before. We used the %d placeholder to read integers from the user. Well, just like printf, scanf can use the %s placeholder that will let it read a string. It skips any white space, then reads everything the user types until the next white space they type. How could that go wrong? Let's play with this example in CLion. This code allocates 10 positions in a char array. That'll be 10 bytes, so we can store strings up to 9 characters long. To show how scanf should work, let's get one string from the user. And this time, I'll just type 5 characters. Print it out between the X's again, and everything looks good. Let's do that again. But this time, I'm declaring an integer b that will hold 42. If we look at that in memory, you can see that here is the string we read and stored in our array, and here is b. Print b. It looks good. Now let's do the scanf again, but this time I'm going to enter 15 characters. That'll require 16 bytes so that we can hold the null terminator. But remember that the place that we're storing the string is only 10 characters long. Scanf doesn't know the length of the space we allocated, so it blissfully stores whatever the user entered. Print the string out and it looks fine. But print out B and it's a mess. Looking at memory shows what happened. Look at how that long user input just splatted itself all over the place, overwriting the place where B was stored. Clearly, using scanf this way is a terrible idea. New rule. Use scanf for reading things other than strings, but we'll need to do something better for strings. Before we find a better way to get strings from a user, let's think about what we just saw again. When I entered too much data, the scanf wrote beyond the space that we had allocated for it. Anytime that happens, not just for strings, it's called buffer overflow. We just watched it corrupt the values of other variables, but this type of vulnerability can be exploited for much more devious things. Remember that return control word that holds the address the function will return to and it's stored at the bottom of the current stack frame? Evildoers could use buffer overflow to overwrite the return control word with an address of their code. Then, when your code returns, it returns to their code instead of yours, and now they have control of your system. This makes C not memory safe, and it is a huge weakness. In fact, there are calls for us to eliminate non-memory safe languages because they are a source of a great majority of security vulnerabilities. Since using scanf to read strings was so very risky, we need something better. C has a function named getS that will get an entire line of input. But that has the same buffer overflow problem that scanf has, so never, ever use getS. The best way to read strings is fgets. It takes 3 parameters: a pointer where you want the string to be stored, a size that is the maximum number of characters that it can read, and a file pointer for where to read from. Standard in means read from the keyboard. Since we give fgets a limit on how many characters it can read, it does not have the buffer overflow problem that scanf and getS had. So the safe way to read strings is to use fgets to read the whole line and then parse it into pieces if you need it. There are a lot of string functions that can help you do that. Look at my shorts to find information on a bunch of them.